Wayne Ottinger began his aerospace career in jet and rocket propulsion in June of 1955. This chart starts with Wayne's heritage and summarizes the time spans of 66 years from the Wright brothers' first flight to the Apollo 11 landing, 87 years from the Wright brothers' first flight to the Hubble telescope, and 114 years if next year's scheduled launch of the James Webb Telescope is met. This was an opportune time just before the space program really took off. This presentation will focus on early spaceflight in the 1950s. As the Cold War heated up after World War II, our space program was greatly stimulated by Russia's launch of the first satellite, Sputnik, on October 4, 1957. U.S. aviation progress after the war brought in the jet age, transforming both military and civilian applications while providing significant growth in employment and economic benefits. Herein are some untold stories of how challenges were met over the past 6 decades of aerospace progress. This clip, shown on the Discovery Channel, is from the great book series, The Right Stuff. In it, the reported interview with Nikita Khrushchev's son, Sergei, about the Cold War is revealing. It certainly is an example of the driving force of fear and suspicion, particularly that generated by the ignorance of true facts. Wayne's cousin, Dale Miner, was the executive producer for this great book series. After serving as an infantryman in the Korean War, Dale became a combat reporter in Vietnam. Following that, he served as a personal writer for Walter Cronkite's broadcast news reports and TV documentaries.
But Russia was still winning the race. Kennedy had a novel solution that Wolf did not include in his book. In Vienna, 6 weeks after Shepard's flight, Kennedy proposed ending the competition by combining the two space programs. Nikita Khrushchev turned him down. Khrushchev used to walk in the evenings with his son, Sergei. Sergei asked his father why he wouldn't cooperate with the Americans. The Russian leader replied,
"It will mean opening up a rocket program to them. We have only 200 missiles, but they think we have many more."
Sergei asked,
"So, when they say we have something to hide?"
Nikita Khrushchev laughed.
It is just the opposite. We have nothing to hide. We have nothing, and we must hide it.
When we're talking about disparity between Soviet Union and the United States, it was huge. Really, Americans in 1955, when my father first met with President Eisenhower in Geneva, had everything, and we had nothing.
Unknown to Western analysts, many of the missiles in the May Day parades, symbols of Russian might, were wooden models. Russia only had 5 that could make it to America. The whole space race was an enormous smokescreen to conceal Russian weakness. And it was working. The space race continued unabated.
Roger, this is Liberty Bell 7. The clock is operating.
This clip is from the HBO documentary of When We Left Earth. It starts with the X-15, which flew first on June 8, 1959, and then ends with Project Mercury, which flew Ham, the chimpanzee, on January 31, 1961, and then Alan Shepard, the astronaut, on May 5th of the same year.
In the high desert of California, NASA tests an experimental rocket plane, the X-15. They want to put a man into space, and they're in a hurry.
Rockets were powering aircraft to higher and higher speeds. The X-15 had enough energy to zoom to altitudes above the atmosphere.
The X-15 flies so high, pilots experience weightlessness and look out into the darkness of space. But even at 600,000 horsepower, it would need to fly 4 times its top speed to put a man into orbit. The Soviet Union holds an early lead in the space race, launching the first unmanned satellite to orbit the Earth.
On October 4th, 1957, when Sputnik went into orbit, people were so upset. They said, these people can't build a refrigerator. How can they get into orbit? How did this happen?
To beat the Soviets, NASA must launch a man into Earth orbit. Only rockets can go fast enough, more than 17,000 miles per hour. They call the program Project Mercury and rally a team of determined young scientists and engineers to figure out how to fly a military missile with a man on top.
Most of us came in from aircraft flight test. We knew nothing about rocketry, we knew nothing about spacecraft, we knew nothing about orbits.
Gene Kranz joins the flight director's team in NASA's earliest days.
So it was a question of learning to drink from a fire hose. We had to learn all about trajectories. I'd never heard the term retrofire, coming on down from orbit, getting the spacecraft back home.
A few weeks after Wayne arrived at the NASA Flight Research Center as the X-15 propulsion engineer, Gary Powers was shot down, as well as a Russian fighter pilot who died trying to intercept Gary's U-2. A U-2 stationed at Edwards in secret was brought to the NASA hangar by the CIA overnight on May 1st, and the tail was painted with the NASA logo. On May 2nd, the chief test pilot, Joe Walker, had to taxi this U-2 for the press conference that morning, having never even seen the airplane before. Later, at the May 17, 1960 Peace Summit in Paris, Khrushchev pounded the table with his shoe, confronting Ike with the physical evidence of the U-2 spy cameras that had been recovered. He rightfully challenged the lie Ike was telling that it was a NASA aircraft on a peaceful mission. Wayne met Powers several years later after Gary's release from the Russian prison on February 10, 1962, in the prisoner swap for Russian spy Rudolf Abel. Powers died in a news helicopter he was piloting on August 1, 1977, in Los Angeles. Edwards Air Force Base was on combat alert with the highest security during these few weeks. Getting on and off the base was quite an experience. Wayne was supposed to have moved to Niagara Falls, Buffalo, New York, with his wife and 4 small sons in August that year, but was on standby till late December, when NASA funding finally came through to get the LRV design and build contract underway at Bell Aerosystems. About 12 engineers and technicians manned the X-15 Mission Control Center, setting early precedents for NASA space operations. This expanded significantly through Mercury, Gemini, Apollo, and then onto the Space Shuttle and the International Space Station programs. The X-15 flight path was planned to pass over a string of dry lake beds for 450 miles in Utah, Nevada, and California. These were to be used as emergency landing sites, a plan which paid off many times. About 130 miles north of Las Vegas, many X-15 missions were launched from the Beatty radar and telemetering site. There, about 12 mission controllers, which always included an X-15 pilot serving as a mission controller, supported the pilot. They were usually taken to Edwards in an Air Force C-130 to conduct the flight mission at Beatty. The frequent cancellations due to weather or equipment failures would send the group scurrying off to Las Vegas, where they would get a couple of rooms to group share and enjoy the free lounge shows. The winners at the tables would host the dinners. Wayne made about 8 or 10 trips to Beatty, half of them ending up in Vegas. This later photo of a C-130 resembles those used to support all uprange X-15 flights. There was always a fire truck and a NASA Jeep equipped with the special tools required to render safe the rocket systems should an emergency landing be made. There were about 29 emergency landings at 4 different emergency lakebed landing sites, many due to engine failure. On board the C-130 were the flight crew of 3, plus 2 paramedics, a flight surgeon, a pressure suit technician, 4 aircraft specialists, and a photographer. About 12 of the mission controllers would hitchhike as standing room only. After landing on a 2,000-foot dirt strip, the crew was loaded into a couple of vehicles and taken over dirt mountain roads to the radar site. Wayne's first assignment on the X-15 program was to stand beside an inspector on the test stand with one of the 1,500-pound thrust chambers running next to his face while he was wearing only safety glasses. This was done in order to examine welds on the check valve for leaks. The X-15 flight research program was ready to start about 20 months before the availability of the 60,000-pound thrust XLR-99 rocket engine that was intended to be used. The innovative solution was to adapt 2 old X-1 XLR-11 rocket engines stacked vertically in the same space. This allowed the airplane to reach Mach 3.5 and 136,500 feet altitude on 41 flights equally shared between the first 2 X-15 aircraft. The assembly of the engine required a crew of several rocket technicians over a month, including a halogen leak tester to verify safe operation. The official 59,000-pound thrust specification for the engine proved a bit conservative, as the real thrust provided was a little over 60,000 pounds. The acoustics were such that it would be fatal for anyone exposed to the intense physical effects, thus requiring everyone to occupy the pillboxes shown in the next slide with their heavy lids clamped closed. Also, this provided protection from the explosion and fire experienced on the X-15 No. 3's early XLR-99 engine ground run. The NASA van identified as NASA 9 and Wayne's serious but comical story concludes in the next 2 slides. The 2 rear pillboxes were located at either side of the rocket engine. The front pillbox was near the cockpit. The chief inspector was in the front pillbox with a couple of technicians. The 2 rear pillboxes each held an inspector and a technician, with Wayne and the crew chief in the left rear. The fully suited inspectors and technicians had temporarily vacated the pillboxes, leaving Wayne and the crew chief without protective gear inside. Unfortunately, the lid was open. And now the serious but comical rest of the story. The NASA X-15 pilot Milt Thompson, in his book At the Edge of Space, published in 1992 by the Smithsonian Institution, wrote about watching Wayne and the crew chief, Larry Barnett, escape the pillbox from the deadly cloud of 90% ammonia rocket fuel that had leaked from the container used to capture vented gas from the aircraft's 1,400-gallon tank. The cloud, totally shutting down any human respiratory system, hit Larry, who was without adequate protection, at the top of the ladder. Outside, the fully suited inspectors and technicians were on the aircraft inspecting the engine after it had an emergency shutdown. Larry fell on Wayne at the bottom of the pillbox, where Wayne had instinctively pulled his 3% filter mask over his communications headset. Larry and Wayne passed each other climbing out of the ladder, seemingly several times. Then, leaping every other stride into the air to get a breath, they headed toward the NASA 9 communications van. There, Milt was hosting the film executives from Frank Sinatra's production company. They were there preparing to start production of the X-15 movie, narrated by Jimmy Stewart. Milt's account in his book that he autographed for Wayne in 1993 stretched the facts of the story a bit when he told about the event 3 decades later. He wrote, "Larry and Wayne ran directly across the exhaust of the engine." This was an embellishment which was totally inaccurate. His account that was accurate was, and I quote, Wayne Ottinger had failed to remove his radio headphones. As he reached the end of the headphone extension cord, the cord snapped taut and stopped his head in mid-flight. His legs and body continued on, however, until he was stretched out flat in mid-air. And now the crowning embellishment. We could hear the thump as he hit the ground over the deafening banshee wail of the rocket engine. He seemed to bounce immediately back into the air on his feet, and he continued running without missing a stride. It was the most hilarious scene I had ever witnessed. It was as humorous as any Charlie Chaplin or Marx Brothers routine that I had ever seen. End of quote. The film executives, besides getting a good look at an X-15 ground firing test of the rocket engine, also got a bit of entertainment. Totally unscripted. Milt's honorary dinner and roast was scheduled to be held on August 6, 1993. Attendees from across the country were on their way when word came of his death. The family decided to hold it anyway in Lancaster, California. Though sad, it was thought by all that it was what Milt would have wished. This was just soon after Wayne had received Milt's autographed book. The 60,000-pound thrust chamber was cooled with a minus 50 degrees Fahrenheit ammonia fuel that was pumped through the 3/8-inch stainless steel tubes forming the structure. These tubes were coated by a rod-fed ceramic material at the factory before the injector assembly was welded onto the front of the chamber. The spalling in the throat area during early operations eventually leaked raw fuel into the chamber, threatening flight safety. Engine repairs using a factory-outdated process took about a year and $1 million per fix, threatening the entire X-15 flight research program. There were only 8 flight engines for the program. Wayne was assigned to research new processes. He selected adapting a new plasma arc process that used a small gun which sprayed pure metal and/or ceramic powders at about 20,000 degrees Fahrenheit. Several research labs were showing great results with gradated coatings. They started with thin coats of pure metal on the tube surface and then sprayed thin layers of hybrid coatings, increasing the ceramic content of each layer till the final product at the flame front was pure ceramic. The obvious solution to Wayne was to utilize this new technology to produce a field repair capability which could take a fully assembled engine and repair it with improved gradated coatings. This promised to make the coatings last much longer than the original Rokide zirconium oxide ceramics. The next 3 slides show the pantograph machine Wayne conceived. With the help of the NASA shops and 9 technicians, they built and demonstrated it to be used for engine field repairs. It was less than 3 months to develop and deliver this new system to the Air Force Engine Maintenance Shop. An Air Force jet engine rollover stand was mechanized to handle the rocket engine and convert it into a pantograph machine. It was designed to ensure that the plasma arc spray gun was held perpendicular to the chamber tubing contour at a constant distance from the tube surface while the engine mounted in the rollover stand was rotating at prescribed rotational speeds and longitudinal travel, much like a lathe. The NASA shops and technicians were superb on this job, working 12-hour shifts for 7 days a week to design, build, and test this pantograph machine. The patent application for this was denied, however, based on prior art, a la a 1928 coating machine for frosted light bulbs. These shops were a real asset to the X-15 joint program partnership between NASA, the Air Force, and the Navy. The Air Force took delivery of the new coating machine and, with the contributions of the industry research labs, fine-tuned the machine controls and processes to optimize the field repairs and maximize engine availability for the 3 research aircraft. A wide range of rocket engine reliability and safety issues plagued the program. One major misdiagnosed problem was the explosion of pressure transducer lines from the engine's 2-stage igniter installed deep inside the maze of plumbing at the injector face. It was first thought that the problem was a bad batch of LockSafe, a lubricant used in assembly of all the engines in the fuel systems. All these engines were torn down and reassembled with, quote, certified new batches of the lubricant. Due to Wayne's failed attempt to get the X-15 grounded on a flight safety argument, he had the machine shop fabricate a complex steel shield to be clamped in place in small pieces around the transducer lines. Wayne wanted to afford some form of protection as these explosions were encountered on a few flights. The eventual and final fix for the problem was not provided until later, when a ground test engine exploded in the test stand, forcing a correct diagnosis and fix. The lower ventral shown here, used on certain missions that required additional directional control, shows a couple of feet of ground clearance as it hangs off the B-52 wing pylon. One can imagine it almost kissing the runway on a landing rollout. X-15 number 2 aborted a flight with Joe Walker as a pilot on March 21, 1961. The abort occurred soon after the B-52 took off with the X-15 on board. Joe Wenzel, the flight operations director, cleared the B-52 with the X-15 to land fully loaded back on the runway soon after takeoff. This decision was an attempt to secure what was thought to be a loose connector in the equipment bay behind the cockpit. It was causing a problem in system telemetering displays in mission control. Upon the B-52 landing fully loaded, including all the rocket fuel on the X-15 and 300 gallons of LOX for top-off in the B-52, it blew every tire on its landing gear and barely made it to the runway turnoff and onto the taxiway. The announcement then came bellowing into the mission control room, telling them there was smoke coming out of the equipment bay. It took only seconds for the NASA 1 mission control room to realize they had an extremely dangerous situation on their hands. Wayne left mission control and headed to the site with a 4-drawer file cabinet full of drawings on the propulsion system and arrived at the aircraft for an all-nighter. Just off the runway, the fire trucks, ambulance, and ground support equipment eventually surrounded the area along with a crack team of experts. The teamwork finally solved the complex challenges of getting about 15,000 pounds of rocket fuel offloaded using no electrical power from the aircraft. They did this also without having the normal access to critical valves, which were blocked by the inability to remove stress panels in the fully loaded condition. Needless to say, no other aborts of fully loaded landings were ever made during the rest of the program. Wayne was in Houston in November 1967 managing the Lunar Landing Training Vehicles or LLTV's preparations for Apollo astronaut training when the fatal X-15 Mike Adams crash occurred. From the B-52 launch of the X-15 at 45,000 feet, Mike climbed to 266,000 feet in 100 seconds. Then, out of control and flying backwards 49 seconds later, after a flawed re-entry, he began an unrecoverable spin 4 seconds later. Impact to the ground took only 4 minutes from launch off the B-52. The accident summary major notes were as follows. An added 4 seconds on rocket shutdown caused 16,000 feet more altitude from the planned 250,000 feet to the final 266,000 feet. An electrical short in an untested wing pod experiment shut down the MH adaptive control system. Pilots stressed caused loss of awareness of critical instrument display in that the dual mode was not recognized. Vertigo diagnosis at burnout was a contributing factor. The result was, in less than 49 seconds after peak altitude, the aircraft was flying backwards along its flight path. 4 seconds later, a spin started, with nose heading straight down, and lasted for 43 seconds. 2 minutes and 20 seconds from max altitude, the aircraft crashed in the desert. 2 weeks later, the film cassette from the cockpit camera was found more than a mile from where the camera was found. This enabled careful preservation and analysis to reconstruct the events, a major contribution to the accident report. Only 4 minutes from launch to impact. This clip starts with the introduction of Neil Armstrong by Alan Stern in the Palo Alto Conference on Early Suborbital Flights, February 27, 2012.
Let me start by introducing Neil, who almost needs no introduction. I'll never forget the day that I joined the NASA Advisory Council. I was a little intimidated by the people on the council, and Eileen Collins, who was the first woman to command a space shuttle flight, walked in the door with me, and she tapped me on the shoulder and she said, "Look at all these people. I don't know a soul. Thank goodness you're here." Made me feel a lot better, but what really relaxed me was when Neil threw me in the water. Right off the bat, he probably doesn't remember, but almost as soon as the meeting began, some technical issue came up to do with the NASA Mars program. Funny, that's in the news again. And before I knew it, Mr. Armstrong had taken the microphone and said, "I'm not sure what I think about this, but I'd like to know what Dr. Stern thinks." And I swallowed real hard, and I guess I'm on the committee now.
It was during this period that the Soviets launched Sputnik. The world would never be the same. NACA became NASA later that year. NACA, the Air Force, and the Navy had concluded several years earlier that the next research aircraft should investigate the flight at substantially higher speeds and structural temperatures. At the time the bids were first solicited in 1954, the fastest any aircraft had flown was Mach 2.44 the previous year, and you already know that aircraft diverged. 2 years later, as you know, the X-2 reached Mach 3. The only 2 flights in aircraft history over Mach 2.1 had lost control. And when supersonic airplanes went faster, they lost stability and they got hotter. To handle the heat, designers had 3 choices: a hot structure, an insulated structure, or a cooled or ablatively cooled structure. The highest temperature that metals which might be suitable for aircraft structure were nickel alloys. They were capable of withstanding working temperatures of 1,200 degrees Fahrenheit, around that area. So it was decided to be most useful. The new research aircraft should be a hot structure and be designed to fly to the maximum practical operating temperature of those metals, which corresponded to a Mach number of about 7. based on our experience up till that time. Flight to Mach 7 was audacious by any standard. Stability, control, aerodynamic heating, hypersonic flow fields, all enormous design challenges. Building an aircraft out of metals that were extremely difficult to machine, an enormous manufacturing challenge. But the Air Force, NASA, and the Navy were certain that was the aircraft they needed. It would be designated the X-15. Okay, notice. This is why I look at the X-15 project differently than Berg-Rutan. The X-15's purpose was to fly fast and hot. The faster and hotter, the better. It was not designed to fly high. But it was obvious to all that an aircraft that could reach these kind of speeds would have enough total energy to zoom above 100 miles altitude. But attaining maximum altitude was not an objective and never contemplated in the design. The X-15 would fly well above the atmosphere, but only as high and as fast as the hot configuration would allow. But flying above the sensible atmosphere would be another design challenge. The X-1B reaction control program had been terminated, as you know, to enable continuing that research in preparation for the X-15. The NACA installed a similar hydrogen peroxide rocket control in the F-104. I flew this airplane frequently to altitudes above 90,000 feet using the peroxide control system. Beginning the test at about Mach 2 and about 40,000 feet, the aircraft was pulled up sharply to a 70 or 80 degree climb angle and simply coasted on a ballistic arc. Above 80,000 feet, the airspeed indicator read 0, and the ailerons, elevator, and rudder were completely ineffective. The windmilling engine, which was shut down, produced substantial gyroscopically induced yaw motions, which provided very good control tests. We gained confidence in our ability to maintain control in a near vacuum, and that control concept was adopted for the X-15. The X-15 fuselage diameter was selected to accommodate a cockpit with a human occupant. Its length would be long enough to hold enough propellant to accelerate to about Mach 7 with a rocket of the best efficiency available. Knowing the approximate weight of the fuselage and its propellants, a wing could be created which would have enough area to produce a reasonable landing speed. The Mach cone dictated that the wing would have a small span and hence a low aspect ratio. The B-52 mothership could carry and launch the X-15 at high subsonic speeds above 40,000 feet. The wingspan of the X-15 was only 22 feet, and the thin wing, which is a 5% wing, had a low aspect ratio and no ailerons. The horizontal all-moving tail was mounted low to provide good control at high angles of attack and moved differentially to provide roll control. That ensured that the flow distortions caused by roll control surface deflections would always be aft of the aircraft. The high Mach number directional stability would be provided by a wedge-shaped vertical tail on both top and bottom of the fuselage. The top half of the upper dorsal fin and the bottom half of the ventral fin were full flying rudders. The bottom rudder which extended below the landing skids, would be jettisoned before landing. One journalist asked Joe Walker, the chief NACA pilot, what would happen if they weren't able to jettison the lower tail, and he said, well, I guess you'd have the fastest plow in the world. Speed brakes were located on the aft portion of each vertical fin, and when extended, would increase directional stability, made a wider wedge. North American Aviation constructed the aircraft in the years 1956 to 59. The planned engine was significantly behind schedule, so the initial flight tests were used two engines from the X-1 program, the XLR-11 engine. Flights above Mach 3 were raising the nose and leading edge temperatures on the wing to above 500 degrees Fahrenheit, confirming the predictions. The planned rocket was the newly designed throttleable 57,000-pound thrust engine using a fuel of anhydrous ammonia and an oxidizer of liquid oxygen. When the big engine was available and installed, the performance envelope was rapidly expanded to Mach 6 and over 200,000 feet. I flew in the second flight of the aircraft above 200,000. Above Mach 5, structural temperatures climbed to above 1,000 degrees Fahrenheit, with hot spots above 1,300 degrees and one measurement at 1,500 degrees Fahrenheit. That's cherry red. High temperature flights at high Mach numbers were at altitudes below 100,000 feet. And high flights, examining techniques above the sensible atmosphere, from flight durations, from drop to landing, were about 10 minutes. Couldn't be considered a time builder. With such short flight times, it became imperative to gather the most possible flight data in the minimum available time. The need was assisted, That need was assisted by the X-15 simulator, which I believe was the largest and most complex analog simulation ever constructed at the time. Aircraft data obtained during the X-15 flights was immediately incorporated into the simulation, making it a true research tool. It was used in the design of the research programs, flight planning, system development, and of course as a pilot training aid. Because the flights were so short, time was money, and the critical data area could be practiced many times by the pilot prior to each flight, maximizing the data return from each maneuver in each flight. The X-15, with its short wings and wedge vertical tails, had a very low lift-drag ratio, which means it descended like a brick. Comfortable landing approach speed was 300 knots. Descent rate on final, something greater than 20,000 feet per minute. Descent rate was slowed at about 1,000-foot altitude, and touchdown was about 200 knots. Velocities and altitudes above the atmosphere were provided by a 3-axis inertial measurement system. On an inertially stabilized platform were mounted accelerometers, and their output was amplified 250,000 times and integrated once with respect to time for velocity, and a second integration with respect to time for position, all analog. Digital computations at that time were far too slow to calculate position and velocity in real time. As the X-15 was the only flying machine flying to these speeds and altitudes, it was called on to carry sensors that were far afield from its initial purpose. measurement of intensity, polarization, and spectral distortion of the daytime sky at high altitude, measurement of energy emissions of various stars in the ultraviolet range, micrometeorite and extraterrestrial dust collection at high altitudes, hypersonic flow field determinations through and around a ramjet or scramjet, development and testing of measurement techniques to determine atmospheric density, drag determination of varied decelerator configurations, leading edge configuration effects on heat transfer, investigation of the Earth horizontal resolution as a function of wavelength and other visible spectrum elements. All in all, it received a remarkable record. 103 aircraft, 199 flights in 9 years. There were 4 significant accidents and 1 death. But there was collected an enormous storehouse of new information on high speed, high temperature, and high altitude flight. I've stitched together a short film of a complete flight to above 300,000 feet, which hopefully will tie together some of the things we've been discussing. And so feel free to ask questions about the film or about anything else while the film is running in the background. And if you're bored with either the film or my answers, you can just direct your attention to the alternate source. Thank you.
Of the 12 pilots that flew the X-15, Major General Joe Engel is the last one living today. During the course of testing, Joe earned his Air Force astronaut wings and a Distinguished Flying Cross. Joe was scheduled to land on the moon as lunar module pilot on Apollo 17, but lost out when he was bumped after Apollo 18 was canceled by Congress, thus making Apollo 17 the final mission in the program. This last mission required a professional geologist, who happened to be Harrison H. Schmitt. Joe went on to subsequently become one of the first astronauts in the Space Shuttle program, and in so doing flight tested the Space Shuttle Enterprise in 1977. To perform the atmospheric landing test, the Enterprise was launched from the top of a highly modified Boeing 747 jet. Later, in 1981, Joe was commander of the second orbital test flight of the Space Shuttle Columbia.
I won't go through all these things. They're pretty standard. They were developed. All these things were developed during the period of time that we were flying the test flights. Down here on the confidence, the groundwork for space shuttle planning. Space separation techniques, they didn't play too much into the space shuttle. We dropped off the bottom of the X-15. We actually flew off the top on the with the space shuttle with Enterprise. But the low LOD, low lift to drag ratio landings, unpowered landings, lift to drag is an easy way to figure, or a simple way to look at lift to drag is that's how flat you can glide an airplane that doesn't have any power. The gliders, sailplanes that the guys fly up here at Tehachapi and stuff, heck, a standard vanilla sailplane will get maybe 30 to 1, a lift to drag ratio of 30 to 1. Competition sailplanes get up over 50 to 1. So that means they can glide 50 feet before they lose 1 foot of altitude. So that's pretty darn good glide ratio. The X-15 we had 4.5, LOVD of 4.5, not too shiny. And in fact, to hold the speed you needed to flare and land, you had to come in at about 15, 16 degrees angle of glide path angle. So, but it was done, and it was done over a long enough period of time, and it was done 199 times so that it was essentially a routine thing, and we had proven that that was not a problem. Same thing with terminal area energy management. When you're at 150,000 feet, Mach 6, Mach 8, if your guidance is no good, can you look out the window and actually make decisions to put you over the field so you'll end up and be able to make an accurate touchdown? And we showed that that was possible to do. We also learned the value that having a chase along too. But the thing down at Houston, when the space shuttle was being conceptually designed, even more than conceptually, once the design was honed in on and they saw what the lift to drag ratio was, they said this isn't going to work. You're going to need turbojet engines to make the flatter, shallower glide approach to landing. And you may need them to get from where you pitch over and find out where you are when you get back in the atmosphere to fly over to where you actually want to land. That would have meant putting a package in the tail end and using probably at least a third of the payload volume and at least half of the payload weight in order to put a propulsion package in with jet fuel and stuff like that. And that would have essentially taken the space shuttle out of the picture as far as being a viable truck or a concept of getting things into space. So we didn't have to do that because we had shown it with the X-15 and because we went and actually used a slide similar to this, showing them that the terminal area energy management at the space shuttle started at about Mach 8 and 150,000 feet. We would routinely start at Mach 6 and 100,000 feet, no matter what kind of profile we were flying. The final approach, when you finally set up to line up with the runway and get your speed and aim point just right so you touch down where you want to touch down, in the space shuttle it was going to be about 12 to 14,000 feet, and it was. The X-15, we were about that. We were 10 to 12,000 feet. The final approach glide slope angle, remember I told you it was about 17 degrees on the X-15. it was 18 to 19 degrees on the space shuttle, so it was the same thing. These were all pretty much the same numbers. Final approach speed was exactly the same. We used the same final approach speed. We had about the same touchdown speed. And this magic lift-to-drag ratio that tells you how steep you have to glide was 4.5 in the X-15. We had 4.7. We had an even better lift-to-drag ratio in the space shuttle. So with this information that we got from the X-15, not only was it good for the engineers, but for the managers, for them to be convinced that, yeah, it was okay to press on with this design without having to go to jet engines to help you get back in, was going to be an okay thing. Now, they did have a lot of the same performance characteristics, but they were a little different in size. This is a scale drawing. X-15 was 50 feet long. The space shuttle was 120 feet long, but the payload bay was 60 feet long. So I like to say that the X-15 would fit in the payload bay of the space shuttle. Jeannie likes to remind me that ain't quite right. Not so fast, big guy, because the X-15 had a 22-foot wingspan, and this was only 15 feet across, so you'd have had to fold the wings up like a Navy airplane to get it in there. But it would have fit. It would fit in the payload bay. Now, I'm going to show you this video clip, which I think is really a neat one. There are some things that I want you to kind of be ready for, and I'll use this guy here, just like I said, make a circle around. When it comes off the hooks, right at the beginning, when the X-15 comes off the hooks of the B-52, Scott Crossfield is flying it on the first powered flight, and he's got the two LR-11 engines in it, so he's got 8 chambers. Not throttleable, but you can turn them on and off so you can get whatever thrust you want. But he's got 8 switches over there, so instead of a throttle coming on board, you know, he's going over here and he's doing all this switching and thinks, got 8 of them going. I can't even talk like a test pilot anymore. Got 8 of them going. You got to talk real cool, like, you know, it's not a big deal. I got 8 of them going. And he was really pinching the damn seat cushion, I know, to make sure he hadn't affected it. He also was wearing an early pressure suit. It's a little different. The helmet really was more different than anything else. That's not a really big deal. There's a line in there that says, Jim said that the X-15 has hit, you know, speed and altitude records that hold to even today. Well, that was true when the film was made. Spaceship One has since exceeded our altitude with the X-15. Not by a lot, but it did exceed it. So that's something. Watch for this nose wheel slap down. The thing I told you about, thing that no pilot likes his friends to see happen on a landing. Every time it lands, you'll see that nose come slapping down. And then on the Mud Lake landing, it'll talk about Jack McKay had an engine partial failure, was unable to get rid of all his fuel, and it starts talking about Mud Lake. Watch real close, because on the landing you're going to be looking at a film from a camera that these were called bug-eye cameras, right on the back of the cockpit, and they would look down the back of the airplane to look at control surfaces to see what they were doing as we would get up above the atmosphere. You'll see from this camera on this side, you're going to be looking right down here, and as soon as he touches down, you're going to see this slab go way up like that, and that's what shoves down. And then watch what happens after that. Jack does a slow roll, except it's on the lake bed. There's a scene in here where it talks about coming back from space. It's not real time; it's going faster than normal time. But one of the airplanes had wingtip pods on with experiments out there. Sometimes a camera, sometimes a sampling device for high altitude or micrometeorite dust to collect micrometeorite dust. But this flight had a camera on. That camera is looking from the wingtip right up along this side of the fuselage. So you're going to see this part of the fuselage through an entry, actually coming out from an entry from space, setting up the pattern all the way down to landing. It'll happen a lot faster than it normally did. But the problem is, space is black, and the airplane was black. So the camera's looking at a black airplane against a black background. It's kind of hard to see until you get down closer to where you can see against the atmosphere, or against the Earth. And I'll wiggle around on that one too. The yaw, needle, and switch we'll talk about when we get into Q&As, because I want to get on to that. And I believe that now is a good time to run the video. Yeah. Isn't that cool? God, they
And
don't
no
go
tail at 33,000 feet. Roger. Looks good across the board. I'm on number 1 and climbing for 35. Right. Direction looks good, Scotty. Right on, you look real good. Okay, fine. Up on 50. Level. Right.
On September 17th, 1959, one of the major stories in all of aerospace history got underway in the skies over Edwards Air Force Base as test pilot Scott Crossfield completed the first powered flight of the North American X-15. No other aircraft before or since has come close to approaching the truly awesome performance of this airplane. Under a joint NASA, Air Force, and Navy program, it was designed to explore the unknowns of hypersonic and exoatmospheric flight, controlled flight at speeds in excess of Mach 5 and to altitudes in excess of 250,000 feet. Its design was tailored to permit it to fly in this extreme environment, to withstand the searing, friction-generated 1,200-degree temperatures of re-entry. Its outer skin was fabricated from a special chrome-nickel alloy called Inconel X. To enable the pilot to maintain precise control as it exited the atmosphere, its nose and wingtips were configured with reaction controls, small hydrogen peroxide jet thrusters to provide pitch, yaw, and roll control. Finally, it was designed around a mammoth, single-chamber, throttleable rocket engine, the 57,000-pound thrust XLR-99. Because of delays in its development, however, the first 25 flights were made with an interim pair of uprated 4-chamber XLR-11s, providing a modest 16,000 pounds of thrust. As North American's pilot, Crossfield's job was to demonstrate the airworthiness of the X-15 and the proper functioning of its systems up to speeds approaching Mach 3. These initial tests were not without their hazards. Shortly after launch on the third powered flight, for example, an engine explosion rocked the airplane. Unable to jettison his fuel and LOX, Crossfield was forced to make an emergency landing with a heavy load of propellants that broke the back of the airplane just behind the cockpit as he touched down. He was uninjured, and the number 2 X-15 was repaired and restored to flight status. Meanwhile, as flight testing proceeded, the first XLR-99 was delivered to Edwards for ground tests. In June of 1960, Crossfield was seated in the cockpit of the number 3 X-15 when a malfunctioning valve caused a catastrophic explosion. Remarkably, once again, he was uninjured, and the airplane was rebuilt. Crossfield completed North American's program when he demonstrated the successful operation of the engine during 3 flights in November and December of 1960. During these flights, however, he'd been contractually limited to speeds just below Mach 3, and thus neither the airplane nor the engine had been taxed to anything close to its full potential, as a small group of government test pilots turned to the job of expanding the X-15's envelope. They included NASA's Joe Walker, Jack McKay, and Neil Armstrong, Air Force Majors Bob White and Bob Rushworth, and Navy Commander Forrest Peterson. The X-15's awesome potential was finally unleashed in the spring of 1961, when within the brief span of 8 months between March and November of that year, it became the first airplane in history to exceed Mach 4, 5, and 6. The man who made those flights, Major Bob White, was also the first to fly it in space, as he climbed above 314,000 feet the following year. And in August of 1963, NASA's Joe Walker took it all the way up to its peak altitude, 354,000 feet, more than 67 miles above the Earth's surface, a record which, to this day, still stands for a winged aircraft. But the program was concerned with much more than dazzling ultra-performance records. Throughout this early phase, the X-15's pilots collected mountains of critical research data on hypersonic stability and control, heating rates, and flight loads, while demonstrating that they could fly a winged vehicle out of the atmosphere, transition from conventional aerodynamic to reaction controls, and then return, and by means of energy management techniques, glide down to precision landings. As the program moved into the mid-60s, its focus shifted toward using the airplanes as testbeds for more generic research on hypersonic phenomena, and to carry a wide variety of space science experiments into the near space environment. By that time, a new group of pilots was coming on board, including the Air Force's Captain Joe Engle, and Majors Pete Knight and Mike Adams, as well as NASA's Bill Dana and Milt Thompson. Each of their missions typically lasted only about 10 minutes, but the mental and physical demands imposed on them during that brief span were truly prodigious. On a typical altitude mission, for example, as the pilot lit the engine, he was slammed back into his seat by an instantaneous 2G acceleration. Pulling into a climb, within mere seconds, he was passing through Mach 3. While being subjected to ever-increasing G-forces during the climb, he had to maintain extraordinarily precise control. Each additional degree of climb angle beyond the planned profile, for example, could produce an increase of 7,500 feet in altitude. Engine burnout occurred 82 seconds after ignition, as he was passing through 150,000 feet at Mach 5. Almost instantaneously, the 4G loads pressing him against his seat plummeted to zero, an experience prompting Milt Thompson to quip that the X-15 was the only airplane he ever flew, where he was glad when the engine quit. In sharp contrast to the tremendous forces which only moments before had pressed so heavily against him, he experienced the freedom of zero gravity as he coasted over the top of his flight path at 280,000 feet. About 3 minutes after exiting the atmosphere, he re-entered it at Mach 5 and started his pull-out at about 150,000 feet. Once again, he had to maintain incredibly precise control of the airplane as the G-forces built up to more than 5 Gs before he came level at 80,000 feet and began to set up his approach into Edwards, about 60 miles distant. Now his focus was on energy management. Technique and skill were critical here, for if he dissipated his speed and altitude too rapidly, he'd fall short of the base. Too slowly, and he'd overshoot it. As he neared Edwards, he banked into a 360-degree spiral approach to the lake bed, where the X-15 touched down at about 230 miles per hour. Not all missions went so smoothly. In November of 1962, Jack McKay lost power shortly after launch in the No. 2 aircraft and was forced to attempt a high-speed emergency landing at nearly 300 miles per hour on Mud Lake in Nevada. At touchdown, the left landing skid collapsed and the craft tumbled violently across the lake bed. Though seriously injured, McKay recovered to fly again. And while the twisted mass of the airplane appeared to be a total loss, it was rebuilt as the X-15A2. Configured with a pair of jettisonable external propellant tanks that would nearly double the engine's burn time and thereby enable it to reach for higher speeds, it was also covered with a thermal protection coating to enable it to withstand the 2,000-degree temperatures predicted at those speeds. On October 3, 1967, Major Pete Knight launched from the B-52, lit his engine, and began to climb, consuming its propellants at a rate of 12,000 pounds per minute. The big engine drained the external tanks in just 67 seconds. And accelerating upward through 70,000 feet at Mach 2, Knight felt a sharp bump as they were jettisoned. Coming level at about 100,000 feet, he flew a perfect profile to a speed of Mach 6.7, 4,520 miles per hour. Flying at a speed more than twice that of a .50 caliber bullet, he was unaware of the ordeal endured by his craft. The thermal protection coating had failed as temperatures exceeded 3,000 degrees, and a dummy ramjet attached to the ventral tail had literally burned off, leaving a hole through which torch-like air was channeled into the X-15's tail section, where it burned out pressurization lines and electrical wiring that prevented him from jettisoning his propellants and lowering his landing flaps. By dint of exceptional piloting skill, he managed to bring the stricken airplane in for a safe landing. Charred by its wild ride through a hypersonic inferno, the X-15A2 would never fly again. And Pete Knight's record still remains the highest speed at which any man has ever flown in an airplane. When Bill Dana climbed out of the cockpit for the final time in October of 1968, it marked the end of a truly remarkable era in flight research. During 199 flights over a nearly 10-year span, the three X-15s had completely redefined the envelope as they mapped out the frontiers of hypersonic flight. 12 pilots had flown the X-15. 8 of them had qualified for astronauts' wings by flying an airplane in space. Sadly, one of them, Major Mike Adams, had lost his life when in November of 1967, the number 3 X-15 departed from controlled flight and broke apart during re-entry. A tragic loss that underscored the risks inherent in flight research. His death marred what is otherwise regarded as, by far, the most successful flight research program in history. Not only did it make major contributions to the more celebrated Mercury, Gemini, and Apollo programs, the knowledge gained from it made it possible for designers to proceed with the development of a true orbiting spaceship. When the space shuttles touched down on Rogers Dry Lake at Edwards more than a decade later, they were the direct beneficiaries of a small rocket plane that first bridged the gap between air and space.
That's some film. That's it. Thank you. I don't get gooey, but I can't overemphasize that closing statement about how much the X-15 contributed to the space shuttle. And you guys here at Dryden, you know, this X-15 is when people think of research rocket airplanes, when they think of research, they think of Dryden. And a lot of times they think of the X-15, and you all ought to be damn proud of that. Both the fact that you're working here at Dryden, where all the flight testing is done, all the real flight testing is done, and will be. And secondly, that you've got the X-15 in your heritage, because it lived right here in the hangar while it was here, all the time it was here.
In addition to Joe's excellent summary of the X-15 contributions on the previous slide, Wayne emphasizes in this slide that the reliable record for pilots' ability to re-enter from space and land dead stick with no power enabled much larger space shuttle payloads to build the International Space Station by eliminating the jet engines required in the preliminary design. In this Bell photo, Wayne was 30 years old. He was assigned for 14 months as the NASA plant representative at the Bell Aerosystems Niagara Falls, New York plant for the Lunar Landing Research Vehicle design, manufacturing, and assembly. Under budget constraints, much of the final assembly and testing was done at the NASA Edwards Air Force Base facilities. To assist in preparations for that first flight, Bell sent about 20 engineers and technicians to the NASA Flight Research Center at Edwards for a 6-month period. Wayne here is flanked by 2 Bell VPs. On his right is General Walter Dornberger, the former Nazi general in charge of the missile works at Peenemünde, Germany during World War II. He was Werner von Braun's boss. This is a short clip from a NASA video titled 300 feet to the moon. It includes the only soundtrack of the operation of the 16 90-pound thrust attitude rockets, the two 500-pound lift rockets used to simulate lunar maneuvering, and the jet engine used to cancel the 5/6 excess Earth gravity. All this was done to create a realistic Earth-bound free flight simulation for lunar landings.
Before an astronaut ever actually flies a LLTV, he is trained in a helicopter for at least 100 hours. He has trained in an LLTV simulator, completing a detailed program, or syllabus, as the pilots call it. He has trained in a vehicle tethered to a large overhead frame. He has handled the LLTV mounted in a fixture where the vehicle will respond to certain flight commands. And he has powered up the LLTV engines, with the vehicle itself tied down, to become accustomed to the operation of the engines. Only after the considerable training, plus many briefings, is he ready to fly the LLTV. And in the total picture, this is but a small part of the training necessary to learn to fly the lunar module itself.
The LLTV training operation at Ellington Field, just north of NASA Houston Complex and 25 miles south of downtown Houston, was integrated with the aircraft operations at the NASA Manned Spacecraft Center, or MSC. NASA's fleet included a large number of T-38 jets, helicopters, and transport aircraft. The base was and is hosted by the Texas Air National Guard's 147th Reconnaissance Wing. From 1962 to 1972, the Apollo Lunar Landing Training Program had 591 flights over its last 8 years. During that period, there were only 3 accidents where the pilots had to eject, all safely, a tribute to the design and operation of the specially crafted, unique ejection system. The first 2 ejections were caused by human error of the ground-based mission control staff. NASA subsequently corrected that by overhauling mission control staffing and procedures. The 3rd ejection was a hardware failure covered in a later slide. Just after the first LLRV's crash, Wayne was sitting next to the pilot, astronaut Neil Armstrong, at the debrief. All there were surprised when Neil's speech was slurring. Neil discovered he had bitten his tongue during the ejection, a much preferred injury to some of the other possibilities. That afternoon, when the crane lifted the wreckage, a snake crawled out from under the vehicle. A subsequent cartoon was made with the caption under the wreckage and over the snake, "What the blankety blank was that?" That was one shook-up reptile. The image on the right is of the sidearm controller from Neil's crashed LLRV. Dean Grimm, the program manager, had this in his basement until he sent it to Wayne in about 2012. Wayne then sent it on to NASA at Edwards, planning to borrow it back from time to time for his STEM lectures. But now, since the NASA Flight Research Center has been renamed after Neil Armstrong, it's under strict control, and the best Wayne can do is get the sidearm controller on loan to CU Boulder. Wayne was a Bell manager in Houston with over 100 engineers and technicians supporting NASA as they conducted all the ground testing and flight testing operations. During this time, there were 3 ejections, 1 LLRV and 2 LLTVs. The first ejection was by astronaut Neil Armstrong. The second ejection was by Joe Algranti, the chief of flight operations for the NASA Manned Spacecraft Center, and the third ejection was by NASA test pilot Stu Present. Later slides will describe the events that caused all 3 of these ejections. The seatman separator or pyrotechnic rotary actuator, fondly called the butt snapper, shown here is the one used in Armstrong's ejection. The ejection was caused by lift rocket fuel exhaustion and inadvertent venting of the helium pressure gas. The actuator, with its harness, was returned from a Bell crew chief in Houston as part of a miscellaneous collection of LLRV parts. X-rays taken of this rotary actuator in 2013 indicated that no propellant remains in the cartridge chamber. Notice the harness the pilot sat on is wound up into the retracted position from the ejection sequence. On December 15, 1965, this sidearm controller flew into space on Gemini 6A, crewed by Wally Schirra and Tom Stafford. This was the first successful rendezvous mission between 2 spacecraft in history. Following its mission, the controller was retrieved by NASA engineer Dean Grimm and sent to NASA Dryden. NASA engineers modified the sidearm controller and installed it in the Lunar Landing Research Vehicle, LLRV number 1. With his right hand, the pilot could control roll, pitch, and yaw thrusters by side to side, fore and aft, and twisting motions of the sidearm controller. The second ejection occurred in 1968 with Joe Algranti as pilot. In a miraculous last 0.3 of a second ejection, he punched out as his LLTV number 1 came out of its violent roll straight and level and then crashed. Joe was uninjured.
NASA then made a major overhaul in their flight operations, adding over 20 mission controllers and an Air Force mobile weather support for all future flights.
This dramatic photo is from the 16mm film of the second Lunar Landing Training Vehicle's successful ejection by pilot Stu Present. It shows the ejection rocket flaming out the jet engine. This was the only hardware failure of the 3 ejections that occurred in the Apollo Lunar Landing Training Program. It was caused by an undetected failure mode of a so-called product improvement by GE of the jet engine's DC generator. The ejection rocket blast flamed out the jet engine, which spun the engine and the DC generator down. Only later was it discovered that the undetected high magnetic field released had disabled the emergency electric bus switchover circuit and kept the battery offline. Failure of the battery to come online and power the flight controls for the vehicle attitude rocket system caused the LLTV to pitch up out of control, necessitating ejection. With no jet engine thrust, it crashed and was destroyed. Later, with the film footage and the telemetering data, it took only a few hours to pin down the cause of the crash. Although Stu survived this crash, he sadly was killed the next year in a T-38 accident. Such is the high-risk life of test pilots and astronauts. On this crew shot, Wayne is second from right. The Gemini 4 mission's first attempt at rendezvous by Jim McDivitt and Ed White on June 3, 1965, failed due to a lack of understanding by the mission planners of the orbital mechanics required to accomplish success. This was a critical requirement for the Apollo program. It was mandatory that these maneuvers be safely accomplished to fulfill the overall mission of getting to the moon. This video clip is taken from a NASA documentary. But first, there is a remarkable story to tell how the challenge was overcome and success achieved on December 15, 1965, just 6½ months later. The next slide is a video clip of Gemini 6A crew, Wally Schirra and Tom Stafford, targeting Gemini 7 in orbit with Frank Borman and Jim Lovell aboard during their 14-day mission. Now for the rest of the story. Dean Grimm had been managing Wayne's LLRV and LLTV programs for the NASA Manned Spacecraft Center, or MSC, now the Johnson Spacecraft Center. He temporarily exited that program and was assigned primary responsibility for developing new orbital mechanics to correct the failure of the first rendezvous attempt made by Gemini 4. Dean told Wayne the following story soon before his death in April 2014. Dean said that NASA MSC at Houston had just installed a $40 million mission simulator, and he requested that they run the rendezvous simulation backwards so he could identify maneuver errors and develop corrective actions. MSC computer experts said no, it could not be done. So Dean contacted his classmate from the University of Kansas who was running the McDonnell Douglas Gemini mission simulator at the St. Louis facility. Dean got a positive response and went through NASA headquarters to get permission to take the 2 astronauts assigned to the next mission to attempt the rendezvous on Gemini 6A Wally and Tom to St. Louis and used that simulator to solve the problem. Dean got the go-ahead, and about 5 months later they presented their solution at NASA headquarters. NASA's red team, Boeing, recommended their solution would not work, and that Boeing be given the task to develop new rendezvous procedures. Dean immediately announced that he would resign from NASA should they accept Boeing's recommendation. Schirra also said he would resign from the mission unless NASA accepted their solution. NASA accepted their solution from the Gemini simulator in St. Louis, and 1 month later, the Gemini 6A mission succeeded. Subsequently, Dean returned to Wayne's LLRV and LLTV program. This is a very good account of how the rendezvous finally succeeded, accelerating the march to Apollo 11.
Gemini 7, Houston. We were wondering if you saw the...
Build up some 430,000 pounds of thrust. T-minus 10, 9, 8, 7, 6.
5, 4, 3, 2, 1, 0. Ignition. Engine start. We have a liftoff.
Gemini 6's actual apogee altitude is 140 nautical miles. The required apogee altitude is 146 nautical miles. To correct this condition, the command pilot will perform a height adjustment maneuver at the end of the first orbit using his aft-firing thrusters. Gemini 7 is now here in a 161 nautical mile circular orbit. Gemini 6 is now here 560 miles behind Gemini 7 in an orbit having an apogee of 146 nautical miles and a perigee of 87 nautical miles. In this present orbit, Gemini 6 would catch up with Gemini 7 in approximately 2 hours. To allow the rendezvous to occur as planned, the catch-up rate will be slowed by 2 maneuvers. The first maneuver will be at second apogee, applied in a posigrade direction to raise the perigee to 117 nautical miles. We cannot expect both spacecraft to be in exactly the same orbital plane. Therefore, at 2 hours and 42 minutes after liftoff, Gemini 6 command pilot Wally Schirra will yaw his spacecraft to the south and execute a plane change maneuver that will place his spacecraft exactly in the same orbit with Gemini 7. Both spacecraft are now in the same orbital plane. Gemini 6, for the second time, will apply thrust at apogee to circularize his orbit at 146 nautical miles and to also slow his catch-up rate. At this point in time, Gemini 6 will be 15 miles below Gemini 7 and 140 miles behind. By this point in time, Gemini 6 should be within radar contact of Gemini 7. When the slant range distance between Gemini 6 and Gemini 7 has been reduced to approximately 32 nautical miles, Gemini 6 will initiate the first of a series of terminal phase maneuvers. These maneuvers are accomplished by the command pilot placing the nose of his spacecraft at his target, Gemini 7, and thrusting along the line of sight. There will be two mid-course correction maneuvers, probably here and here. These maneuvers will place him on a trajectory that will be slightly below and in front of Gemini 7. At this point, he will perform a velocity match or braking maneuver that will bring about rendezvous
on us as well.
Break at 0.48 nautical miles, 660 feet.
ジェミ6号と7号の距離はですね、大体
300 feet. We're directly below them. 180 feet. 120 feet. Holding 120 feet, Wally.
ランデブーに成功。ランデブー成功です。Ask them what their range is now.
About 20 feet.
Yeah, we're sitting up here playing bridge together. We're in formation with 7. Everything is go here.
Roger, congratulations. Excellent.
Thank you. It was a lot of fun. Rendezvous and docking are most essential to complete the Apollo lunar mission. Now, on this mission with Gemini 7, we in 6 came within about a foot of Gemini 7.
Perhaps one of the LLRV program's most important challenges was to provide invaluable design data to Grumman for the Lunar Module, or LEM, flight controls. The challenge was to establish, through flight research testing, how low of control authority the Attitude Rocket Control System could go and still provide adequate pilot control for the real lunar landings. This, in turn, meant managing the dry and wet center of gravity for all LLRV flight conditions to very tight tolerances within a half-inch sphere. The propellant feed system for supplying rocket fuel to the 16 90-pound Attitude rockets, the two 500-pound normal lift rockets used for lunar sim mode, and the 6 additional 500-pound emergency lift rockets had to be installed symmetrically on the vehicle. This was to provide balanced propellant feed from the 2 hydrogen peroxide tanks mounted on the pitch axis of the vehicle. The same challenge, but easier, applied to the jet engine fuel tanks on the roll axis. Dry weight vehicle unbalance plus unbalanced fuel consumption had to be tightly controlled to provide quality handling data that was needed. Using scales, clinometers, and a complex set of procedures, the measurement of the center of gravity of the LLRV was made to an accuracy of 1/10 of 1 inch in all 3 axes. This was essential to provide safe flight operations to explore very low flight control system levels of authority in support of Grumman's LEM design. Each of the 4 Attitude rocket clusters used 4 ground-adjustable 18 to 90-pound thrusters, 2 rockets for pitch and roll, which were primary and test, and 2 for yaw, which were primary and test. This picture shows the 4 500-pound lift rockets on the left side of the vehicle, and next to the 300-gallon hydrogen peroxide tank on the pitch axis. To the right of the rockets is the jet engine's front fan engine inlet and engine mount. In the year 2000, the Joe Walker Intermediate School in Lancaster, California approached Wayne to work with their science class to replace the stolen model of the LLRV that Joe's widow had donated to the school. Wayne recruited 2 LLRV crew chiefs and his rocket shop technician to assist him in tutoring the 7 teams of students to build a suitable replacement. That year's project culminated in the schools earning Wayne's donated tile mural for their library. The mural, 5 feet by 9 feet, depicted their activities. They earned the mural by creating the slogan, Learn math and science, one small step for schools across the nation, one giant leap for our future. All 60 students were given poster-sized canvas copies of the mural with a certificate that Neil and Wayne created. Joe Walker was Neil's boss before he became an astronaut. Both were featured in the mural. Neil suggested Wayne get a retired teacher to help with his writing skills for this certificate. Wayne responded he was married to one. Here is a slide of the Gemini 8 emergency landing in the Pacific Ocean, a couple of hundred miles off Okinawa. The spacecraft's control rocket fuel was exhausted due to a stuck thruster. This spun the docked Gemini and Agena spacecrafts to very high rotational speeds, which the crew finally got stopped by undocking and shutting down the stuck rocket. Now for the rest of the story. A couple of months after the Gemini 8 mission, Neil Armstrong was visiting the Bell Aerosystems plant in Niagara Falls. Ken Levine and his spouse, Wilda, and Wayne with his spouse, Sandra, took Neil to dinner in the new Seagram's Tower, a rotating restaurant overlooking Horseshoe Falls in Canada. Neil told them the story of the first docking and their subsequent emergency landing in the Pacific. The emergency was caused by the excessive use of fuel by a stuck rocket in the Gemini capsule. It started the docked Gemini with the Agena rocket to spin. The spin continued accelerating after they separated from the Agena, and by that time they could only scan the switches and instruments in their capsule by rotating their eyeballs. Turning their heads was too painful due to the G's induced by the high spin rate. By the time they got the stuck rocket turned off, they had to abort the scheduled landing in the Atlantic and land earlier in the Pacific. The closest ship was 3 hours away from their landing site in 28-foot seas. When Wayne recently checked the NASA website records, the images of the state of the seas did not match the story. Then he realized he was the only living survivor of that dinner in 1966. As Wayne thought about it, it dawned on him that his recent emails with Dave Scott, Neil's partner in the Gemini 8 capsule, would be a great source to verify his memory of Neil's story. Dave responded and verified his story in this email on August 10, 2015. Wayne, you have a better memory than NASA of today, not surprisingly. We were picked up by the destroyer USS Mason approximately 3 hours after splashdown, and the problem with the sea state was the unreported about 20-foot swells. Perhaps the best source of the story can be found at NASA's website, Official Gemini 8 Report. Keep at it with your memoirs. You have many good stories to tell. Best, Dave. This comparison illustrates the vehicle pitch attitudes required in a typical braking maneuver as preparation for a vertical landing. As Neil Armstrong said in his foreword in the NASA monograph publication titled Unconventional, Contrary, and Ugly, the Lunar Landing Research Vehicle, co-authored by Wayne Ottinger, and I quote, "Landing a craft on the moon was in a number of ways quite different from landing on Earth. The lunar gravitational field is much weaker than Earth's, and there were no runways, lights, radio beacons, or navigational aids of any kind. The moon had no atmosphere. Airplane wings or helicopter rotors would not support the craft. The type of controls used conventionally on Earth-based aircraft could not be used. The lack of an atmosphere also meant that conventional flying instrumentation reflecting airspeed and altitude and rate of climb and descent would be useless because it relied on static and dynamic air pressure to measure changes, something lacking on the moon's surface." This plot of the LEM's actual manually controlled pitch maneuvers performed by Neil, contrasted to the dotted line of a projected automatic landing path, illustrates the value of the LLRV and LLTV flying experience that he received. He knew what to expect with the slow maneuvering rates over the rugged surface of the moon while running low on rocket fuel. Landing in a crater or on a boulder would be fatal. and had to be avoided. Even with today's improved systems automating hazard avoidance, it is doubtful that future landings will be attempted without the astronauts' ability to provide manual control. Using manual controls are much safer than having to abort from an automatic system failure abruptly in the last critical maneuvers. Therefore, the future training protocol will almost surely follow the Apollo experience of so many years ago. As Neil Armstrong stated in his speech to the Society of Experimental Test Pilots Symposium in Anaheim, California on September 29, 2007, and I quote, "The United States is planning to return to the moon, perhaps as early as 2019. When that craft is on final approach to that flat-topped ridge near Shackleton Crater, I hope the person at the controls has had a simulation experience that is at least as good as the LLTV provided the Apollo crews a half-century earlier." The gimbal jet design, together with this ingenious combination of 4 simple sensors, provided the critical path enabling earthbound and free-flight training for the moon landings. The flight dynamics of helicopters here on the Earth, flying in an atmosphere with aerodynamic forces, was totally inadequate for training. Thus, the LLRVs and LLTVs succeeded in flying on the Earth as if they were in a vacuum with no atmosphere and in the 1/6 gravity field found on the moon. On December 9, 2008, the 4 Apollo astronauts, Neil Armstrong, Apollo 11 commander on the left, Gene Cernan, Apollo 17 commander on the right, Harrison Jack Schmitt, Apollo 17 LEM pilot in the background, John Young, Apollo 16 commander not shown, and Wayne Ottinger, LLRV project engineer and LLTV technical director in the center, all briefed the NASA Constellation Altair Lunar Lander Project Office on the LLRV and LLTV programs. Their recommendations were to provide the Constellation program with a free flight LLTV designed and built with the new technologies available today, a half-century since the Apollo program. On March 6, 2016, Gene Cernan was present in Boulder, Colorado for the last day of the Boulder International 2016 Film Festival, where his new film, Last Man on the Moon, was presented. After the showing of the film and a 30-minute Q&A, Wayne and Gene were able to reconnect briefly. In July 2007, Wayne assisted Neil Armstrong's preparation for his presentation to the Society of Experimental Test Pilots Symposium in Anaheim, California on September 29, 2007. NASA excerpted a summary of that presentation in this short clip.
I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth. No single space.
Soon after President Kennedy's call to go to the moon in 1961, a number of researchers began to think about the various aspects of a lunar flight. NASA's Flight Research Center at Edwards proposed a free flight Lunar Landing Simulator program. The research test vehicle was intended to investigate the inherent problems of lunar descents where there is no drag and weight is only 1/6 of Earth. The proposed technique for simulating the lunar gravity installed a jet engine underneath or within the machine on gimbals, so the thrust was always vertically upward. The engine thrust would then be adjusted so that the craft's net weight, that is its gross weight minus the engine thrust, would equal its lunar equivalent. The force required to lift the net weight would be provided by throttleable rockets. The first flight of the LLRV in October of '64 was flown by Joe Walker. First liftoff was what you might call tentative. The second was considerably smoother, During the following year, Joe Walker and Don Malik flew about 150 development flights, expanding the flight envelope and investigating the adequacy of the design and the systems. An advanced version of the LLRV, the Lunar Landing Training Vehicle, or LLTV, proved to be an excellent simulator and was highly regarded by the Apollo lunar module crews as necessary to lunar landing preparation. Typically, the pilot took off with the gimbals locked, flew out to the inner marker, which in this case was about 400 to 500 feet altitude, about a quarter of a mile from the intended touchdown spot. Arriving at the IP, he began a descent toward the target, switched into the lunar simulation mode, energized the lift rockets, and practiced the lunar landing. I was most fortunate to be involved throughout the entire lunar flying development. I had the pleasure of flying every one of the machines, the LLRF, the ground-based simulators, the LLRV, the LLTV, the lunar module, and even the Weber ejection seat, the last not by choice. NASA management was forever worried about the reliability and safety of these machines and continually wanted to shut them down. But the pilots insisted they were vital to lunar landing preparation, and they prevailed.
Drift into the right a little. Good. Safe. Contact light. Okay, engine stop. We copy you down, Eagle. Tranquility Base here. The Eagle has landed.
Thank you, Neil, Buzz, and Mike. We're standing on your shoulders, building on your historic achievements. That drive to reach higher is alive and well in today's astronauts, who will travel aboard Orion on our very challenging path to Mars.
This took place in Houston on December 9, 2008. Gene won the bet as Neil passed on August 22, 2012. Gene followed this year on January 16, 2017. We wish them Godspeed on their greatest adventure, their homebound flight.
It won't be long, and there's going to be fewer of us here. And if you waited another 5 years, you may not have as many of us to talk to. Another 10 years, probably less than that. And God knows in 20 years, we'll be looking down from somewhere, I suppose, watching what you do. And looking at me down. I tell you what, if you're here in 10 years, I'll be here in 10 years. Because you were first on the moon. All I did was follow in your footsteps, so that's the way it's going to be from here on out.
I hope Gene is absolutely right about the timing and how long they're going to be around, but I just want to share with you that out of a number of key people, we're losing them at 3 or 4 a year on this program. Either Alzheimer's or death, and it's the sense of urgency on me it's very urgent to capture and get all this feedback as early as we can.